Okay, the last time, you know that I was English very an online talk. So from today, I want to start exactly where I stopped there. So finishing a bit in the idea of formalism, so that I want to clarify some concept that I didn't explain last time. So the last time I stopped exactly to find the some bracket between the constraints that arise from the Hamiltonian theory, and just to remind you that with this notation, I say that this is the smeared spatial or say diffeomorphism constraint with a test function that in our case is the shift vector. Sorry, the shift vector for the spatial constraint. And we have three Poisson brackets between the diffeomorphism and the diffeomorphism itself, diffeomorphism and the scalar, and between the two scalars. Okay, and this was zero, of course, because this is again a constraint. So it just shifted the shift vector, and the other one was with the smeared scalar. Okay, so we have the here. And the last one being the scalar. Where this S here in a component depends on the metric tensor. Okay. So as I told, this has just the meaning of shifting itself, and this instead is just the meaning that again drags the loss function along the by Lee along the shift vector, and here instead it's something a little more fancy, that at least it's not simply comprehensible in the sense that here the two Hamiltonian constraints in the Poisson bracket that gives instead the vector or the diffeomorphism constraint, taking this here with this vector itself. That basically means that it shifts along the time direction of the collation that we defined. Remember.
Could you just explain the notation a little bit more? I don't remember what all of these things are.
Yeah. Okay. This is, of course, the metric tensor and the components on the sigma. This is on the just space-like surface. The n or n here. That's those are two lapse function the loss function that comes from exactly the 3+1 splitting. That is,
Why do you have two? Why do you have two?
well, these are actually arbitrary functions, but the point is that also I remind you that the total Hamiltonian constraint consists of two constraints, which is this constraint and this constraint.
So what are they?
But-
That's also confusing. And M and N and some are on the bar, some are not on the bar.
Yeah,
So
no,
we'll
well,
just
yeah,
repeat the definitions.
well, this H is the smeared log and AB of the diffeomorphism constraint.
So N is an arbitrary
Test function.
test function.
Yes.
But
But
don't you mean an underbar? H?
yeah,
So what the underbar means vector.
well, also the point is that the total constraint is the sum of this part and also this part here, where here instead is the other scalar constraint. And yeah, in the action that we got, actually a naive shift vector is a Lagrange multiplier. So actually, yeah, it's free. It's not constrained, and this is the Laps function. So, well, it makes sense to give also a meaning of the shift and Laps in the smeared that could be arbitrary.
Maybe in more common language, the first one is called the smeared diffeom constraint.
Yeah.
Smeared is a vector field, and the second one, the Hamiltonian constraint smeared with a Laps function.
Yeah.
But you also left-hand side with just two different choices of Laps functions in this SA. Different type of functions.
Yeah, okay, yeah,
Well,
well,
basically-
that's not M bar B, but it's a derivative of M scalar, right? It's, yeah, right. I mean, otherwise there will be, Laps function and Laps vector, M and N, so there will be more choices. So is it a derivative or a vector?
You mean this?
No,
No,
in the S, in the definition of S,
Yeah.
does it depend on
Yeah, this is the
vector or
yeah, this is the partial derivative of the,
just a partial?
yeah. Um. So from this, we see that they close in the sense that there was some bracket between all the combination of the constraint give again a constraint, which is weakly zero. And I also remind you that these Hamiltonian and default constraints are secondary constraints. That the secondary constraints come just from the consistency of the first, of the primary constraints. The primary constraints were the momentum of the Laps and shift to be zero, and by consistency of this, that is that they are not dynamical variables. We have from that mechanism that the default and scalar constraints arise. Okay, so they're called secondary constraints, because basically that's the second step. And when the Poisson bracket between the constraints give again another constraints which vanishes on the constant surface, they're called the first class constraints. Okay, so the first class constraints are much more powerful than the second class constraints, which the secondary class constraints are everything else, in the sense that we don't get another combination of the constraints. Okay, what is the plus property that the first class constraints have? Well, the point is that when we have constraints, then of course for every component of the constraints, we get rid of 1 degree of freedom on the theory. Instead, the first class constraints, since exactly they are constraints and describe a surface, a submanifold of the phase space, so that we are basically moving along the same all around the submanifold. We have some more constraints from that. It is exactly from basically this one. That is the fact that they're again combination of themselves gives you other constraints. Constraint in the sense that we can get rid of some more degrees of freedom. And you know that the first class constraints get rid of the double of the degrees of freedom of the secondary class constraints. So basically, since we have, well, we cannot see from this number one because actually we can't see the component here, but you know, remember that we have H, which is one constant, and the HA, since A runs from 1 to 3, then we have 4 constraints, okay, for each component. Of course, at fixed x momentum. And so the first class constant gives double, so that instead of 4, we have 8 degrees of freedom that can be removed. And if we count the degrees of freedom, well, we have QAB. Well, I mean the degrees of freedom of the phase space particles. QAB is a 3 by 3 symmetric matrix, so we have 6 degrees of freedom in it. We have also PAB, which is its conjugate, and again, this is symmetric, 3 by 3, so again, we have 6. And then we have the constraints, and the constraints say HAH, and we have 3 degrees of freedom here and 1. But since they are first class constraints, they give 4 by 2, 8 degrees of freedom. And here, instead, we have 5 degrees of freedom. So basically, we have in total 12 minus 8 4 degrees of freedom from the theory. And well, just you know, some fancy remark. This we are in here in the 3+1 theory, so 4-dimensional space-time. If we take, for example, the 2D gravity, we know that it's a topological theory, so there is no degrees of freedom in it. And this can be seen exactly from this study of degrees of freedom, because in that case, A and B run from 1 to 2, so we have 2 by 2 symmetric matrix, which has 3 degrees of freedom. So in the 2D gravity here, QB3, P again 3, HA are 2, and here H 1. Okay. So in total here we have 6 degrees of freedom.
Why is HA2 in 2D?
Well, no, I'm taking only, yeah, exactly. No,
So it's 3D.
no, I mean 2.
3D gravity. You're doing 4D gravity here.
Yeah.
Or are you doing 3D gravity?
Yeah, I mean just the dimension of the space, not the space time. Or just here we have 3 by 2, and again 6. So we have exactly 0 degrees of freedom. That's not something unusual. All right.
So you're not using or advocating the picture that you're fixing gauge degrees of freedom.
Well, no.
That's the sort of usual interpretation of these
Yeah, of course.
first class constraints that they are gauge geometry. So if you solve them and also fix the gauge, that's very good.
Same. We use only when we fix the gauge only afterward. In another formalism, not in the ADM here, because in that case it's crucial in constructing the quantum theory, correct quantum theory. So just the last remark, I just claimed that H bar there generated diffeomorphism. That's why we call it this diffeomorphism concept. But you may say, well, I cannot see it. Of course, yeah, the Poisson bracket gives you a hint, but we want to show exactly that that generates diffeomorphisms in the phase space. So to that end, let's compute just beginning the variation of our function of the phase space variables.
I think that there will be about
What to be there? So just a variation of some function of the phase space variables, e x q x, okay, and computer I just write p and q omitting x, okay, and this is defined as phi of p plus delta p and q plus delta q, of course, evaluate the same point x. And this is, of course, delta phi delta b. That's here. I want to stress it. Now, this variation of the tensors are not variation with respect to its circumvention, but it's functional variation. Okay. By that I mean that delta QAB context by the Q prime AB x minus Q will be at the same context. Okay, and now this one, how can we compute this such a difference? Well, we know how to when we change the coordinates, how a tensor changes. Okay, so basically the steps are the following. We also have the variation of say that we make an infinitesimal transformation of the coordinates, so that we have x prime a defined as x a prime and a, where an a is exactly our shift vector, and we take it to be infinitesimal. Yeah, I could also add some epsilon here, but I just want to take the line connotation, so that just consider this to be a very small displacement. Okay, and when we do this, we know how the tensor changes with such a transformation, and well, it's not complicated, of course, but it takes a little time. If you're someone is interested somehow, I can do it at the end of this talk. Just give you that the final result is of course everything at the point x. So this functional variation corresponds exactly. You can recognize such terms here, and that's exactly the Lie derivative of the metric tensor along a vector field M. So this corresponds to such a Lie derivative. And applying the same.
Why did we change the notation? Our third vectors were underlined. Let's just use underline.
For what? I mean,
Well, so you wrote the Lie derivative up there,
Yeah.
with respect to h, underline.
yeah.
Now you wrote an arrow instead, so maybe we just keep one notation.
Yeah, you're right. Yeah, you're right. That's
Can I also ask about
Yeah.
correlation? Can you please remind me, when you have a prime, it does not mean derivative with respect to x.
no. That's just coordinate transformation.
Okay.
So it's just a new coordinate.
And the derivative is when you write, for example, QAB/C.
Yeah, this is the partial. I mean,
Okay.
I use the general relativity notation you mentioned. That's just the partial derivative with respect to the xc with component c.
Okay, good, thank you.
And right here. And we can do the same thing to p of x, and we can expect that it gives the Lie derivative of the p tensor density of weight 1. When you get this is a tensor density of weight 1. And by weight 1, I mean that contains the square root of the determinant of the metric. And the metric that we are using is 2. Just to, Okay, so actually we can make use of these two variations here. Yeah, so yeah. So our delta phi okay, and now we just stop for a while in the sense that okay cannot be partially reduced. Why do we need this? Well, because I want to compute the Poisson bracket between the in our case between the diffeomorphism constant and the arbitrary function phi of the phase space. And why it's important? Well, because we know that we have a well-defined symplectic structure comes from Q and P. Okay, so that the symplectic Q form will be just the Q wedge the P. From that, we can construct the Poisson brackets, as we know, as partial derivatives, and also, you know that the Poisson bracket are well defined when we have a well-defined Hamiltonian vector field. Okay, by Hamiltonian vector field, I mean that for arbitrary function, say h of the phase space variable called the Hamiltonian function, then we can compute the Hamiltonian vector field. And from that, we can construct Poisson brackets. And we know that Poisson brackets between two functions on the phase space is equivalent to compute the action of the Hamiltonian vector field as associated to a certain Hamiltonian function on another function. And then that gives us exactly the meaning of the Poisson bracket between the vector constraints and a function. It is the action of the Hamiltonian vector field, that's the vector constant, the vector or diffeomorphism constant on a function. Okay. What's that said? So but lastly, I need also another formula. That is this here constraint is exactly where HA was exactly -2 and Q A C D B B B C. Okay, so without integral and a, of course. And also remind you that this is the covariant derivative compatible with Q, Q, and that's torsion free. That's Lepsch interconnection. Now, yeah, we want to calculate the variation of this mirrored constant, the variation with respect to the metric tensor and its conjugate momentum. Because in the Poisson bracket, we have exactly the variation of that with respect to the two variables. But in order to do that, we actually want to write this differently. The point is that we know that D is Q compatible, so actually the action of D on the metric tensor is 0. So we want to perform integration by part so that we have the D on all of these part. And plus 2 and only on NA, because I told you that on Q is 0. So we have Q, A, C, and A. Now it can be proven that since this is a divergence, so that can be also put in as a surface integral. Then that's a boundary term which vanishes.
What do you mean? What is the surface?
Yeah, I mean that this is in pure space-time exactly the divergence of, that we have the contraction between A and C. So what remains here is just the contraction between this and a vector with B, only B, okay. So that's the divergence in pure space-time. And by Stokes theorem, it's just, can be put as a surface integral along the.
Is it still, if the geometry is non-trivial, is it just a surface integral?
Well, because we are in pure space-time and we have this covariant derivative,
right?
So yes, it is.
I think the question is if the theorem holds, if sigma is not opposed.
No, well,
It's not opposed.
So if there's like a well-defined boundary.
If I calculate this term, so there's a partial derivative on this, and then there's a connection piece on this.
Yeah.
So the partial derivative, Stokes theorem, fine. What about the connection piece? Why is that? Why is that the surface term?
Well, because here actually we have tensor density of weight 1. We have the square root of the cube of the metric tensor. So actually, it should goes away because they compensate each other. That is, we have the connection from PB, okay, but we also have to, for a tensor that's the weight 1, we have also minus the contraction of the connection itself, right? it's not.
So,
I mean that if we
It makes sense because if you're doing like a divergence, right, then the connection phase will have two indices contracted.
yeah
And that can be written as a derivative of the logarithm of the determinant of the metric. But that also sits inside the P because it is like the square root of
yeah
the metric. So you will have two contributions, and since one's with a minus, one's with a plus,
yeah what,
they have the same coefficient.
yeah from the tensor with one we have the minus, and since this is a contravariant, we have the plus with the connection, right? So they cancel out. And if we have T as let's say alpha blah blah alpha n of weight 1, actually
well, I mean, the usual way there would be a square root determinant in the measure. Square root determinant of metric in the measure.
yeah, but I tell you that because it's
So it's equivalent T now.
yeah
It's
it's
on the other side of the derivative. That's changed.
Yeah, but I guess it just means that that piece of the connection just cancels out, so you can replace that derivative by a usual partial derivative. I think that's what he's saying.
I mean the extra
The connection
stuff, basically.
but yeah. A bit different, but okay.
well, maybe it's confusing because the square root of the matrix sits in here, you can't see it.
Right.
But of course, it can also always be put here because yes.
Right, right, okay, yeah, that makes sense. Yeah, it's matrix. Mhm.
And for asymptotically flat space-time, it's well, we know that the metric for asymptotic flat space decays as 1 over r, where r is the radius of the of space. And its conjugate momentum can be proven to be decaying as 1 over the square of r, so 1 over r2. The shift vector has 1 over r. And so, and we have also a derivative. So we can see that this decays as 1 over r to the fifth. And so, of course, it's 0, right? Because here we have only r squared and 1 over r cubed. So this is a boundary term that can be neglected, and we have only this one. And of course, we can also put this q inside the covariant derivative, so that it contracts with an a. So D, B, and C, and PBC. Right. Just because I prefer to write with so now we see that since P is symmetric in AB, it has to be symmetric also in this other two integers here. So actually, this is symmetrization of all weight. And you can recognize that such symmetrization is exactly the derivative, again, of the metric. along n.
N is weight 0.
Hmm?
What is the weight of N?
The weight. No, the weight is 0. Yeah, because n doesn't depend on the phase space variables. That's a Lagrange multiplier. Actually, yeah, it's well, twice such symmetrization is the leader derivative. Of course, we can see because when we have the Killing equation, you know that we have the symmetrization of such covariant derivative on a vector field, and we also know that the Killing vector field can be written as the Lie derivative of the metric, because it has a symmetry of the metric. So that's exactly the other way we want to write this H n. But well, when we vary this H with respect to P, of course, since this doesn't depend on P, well, we have just such a variation and everything is fine. But when we want to calculate the variation of this with respect to the metric, actually written in this way, it's a problem. Because then in the Lie derivative, we'll get basically the partial derivative of the Dirac deltas. And that's something that we don't want to have written in that way. So what we can do is just to use a property of the Lie derivative on the tensor product between tensors. That is, that the Lie derivative, say, vector field x, generically, x on a tensor B, where A, B are two arbitrary RQ tensors, as A tensor B plus B tensor of X B. That is, it satisfies this analogous Leibniz rule with the tensor product. So why we want this? Because actually we want to perform again integration by part, so that we will get the Lie derivative of the tensor product between P and Q, and then minus, of course, the Lie derivative on P. That's the way, in the sense that we want to write this Ln of PQ written actually as a tensor product of components AB. Okay, so we have such tensor product, and then we have the two respective components, and that will be a the contraction of two tensors. And this is exactly then by using the formula of QAB and the tensor product with PAB, okay, plus And now also we want to say so that okay, this becomes this minus this, and that's okay. But then we have to compute also this. That's a contraction. So actually, this is 0. It's a scalar, right? It's a scalar of weight 1 because here in P we have square root of 2 of the determinant of the measure. So it will be, if we want to write this is analogous to this one here, and this is analogous to writing this with f as 0, 0 tensor of weight 1. And yeah, this then comes just the f comma a. This is for the the usual derivative, but then since it's a scalar density of weight 1, we have also the additional term. That's the contraction between NA with its partial derivative. Okay, that's basically we can see that we can say that this is analogous to the covariant derivative of some tensor of weight 1, but with the opposite sign, with plus. Okay, this is the derivative of a tensor scalar of weight 1. And so this can be written actually as an A f comma a. But now such a partial derivative can be also written as its covariant derivative. And the answer is yes, because when we have the covariant derivative dA on NAF, then actually it's the covariant derivative on NA, that's NA comma AF plus gamma AAB and BF. And then we have dA on F, which is
You can raise the blackboard.
Hmm?
You can raise
It's the same thing we're discussing
Yeah,
for the service.
you can raise the blackboard a bit so you don't have to sit down.
So here again, comma A, and then since F is of weight 1, it gives minus NA gamma, let's say this is B A F. Okay, or just changing the indices is equal to B A. Okay, so this and this is away, and so this can be written as the covariant derivative. And now, again, we have then the integral of a covariant derivative. Again, with a tensor of root 1. And that's the same stuff. This is a boundary term and it gives 0. Okay, so this term here actually is 0.
Well,
That,
not that term, the integral.
yeah, sure, yeah. Yeah, thank you, that's fine. The integral is 0, yes. So at the end of the day, we can say that the integral of this equal to minus the integral of this. So this is just to say that this is also equal to minus this. I thought that it took more time, but actually it's better not to commit the same mistake twice. So yeah, now I just want to cancel this, separate this, because otherwise it's too stark there. Okay, and now, okay, once we have this, and we have also the variation of the phi, then we can compute here and yeah, this is just the result of sigma of the variation yeah, and this actually well, just be careful because this is on the phase space at the point x. Okay, so it depends on P and Q at the point x. Just and then yeah, of course we leave this and this as they are, and we want just to use substitute these two in the h when we vary this and this with respect to the metric and its conjugate. Okay. And now the variation of h with respect to p gives exactly the derivative. And on the other hand, the variation of this with respect to the metric gives the derivative of p. So this will give delta phi x of yeah p q z minus sorry, with the plus, because then the variation of this with respect to q contains the minus here. Oh, yeah, AB to the point Z. Okay. And so now, the last thing is to write this as actually with the Dirac delta of x minus z, so that instead of having delta phi at the point x, we have it at the point z. That's the same stuff. So at the end of the day, when we choose that Dirac delta and we integrate out the Dirac delta, what we have is just the resulting of such an integration at the point x. So that this becomes delta phi of x of delta q a b point x, so everything in the point x. All right, and so we see that this is exactly this variation of phi. So in this sense, the Poisson bracket corresponds to the variation of phase-space function. And actually, what is also this one? Well, this is exactly the lead derivative of the function along n. This of phi. PAQ to the point x. So actually, what we get here is exactly that the meaning of these constraints is to shift by Lie, to drag by Lie, by an amount n along the vector n of the function itself. So this gives us exactly the right choice to call it the differentiation constraint. That's the origin of it.
Yeah, so the point is that it's not an arbitrary delta phi, it doesn't give you a variation of phi, it gives you a diffeomorphism. It's not any delta phi, it's a diffeomorphism.
Yeah, that's but you want to say that this doesn't have to be the shift vector itself.
No, I'm saying, I mean, the n is just, it's arbitrary anyway.
Yeah. Yes.
But you said that, see, the Poisson, you said the Poisson bracket gives a variation of phi.
Yeah.
But the variation of phi is completely general.
Yes.
But this is not completely general. This is a particular delta phi,
well,
which is a diffeomorphism, which is what you said.
I never said that Poisson bracket gives a general variation.
Well, you said it like it could. Well, let's say you didn't mean it, but the way you said it, it sounded like it could be interpreted.
Well, maybe you're referring to the fact that the Poisson bracket can be also written as the action of the Hamiltonian vector field on a function, right? Maybe.
No. I was just reacting to the way you phrased, not in the end, but like 2 minutes before.
Okay, no, well, yeah, so I want to clarify if I'm mistaken. That, of course, the delta phi arbitrarily speaking is just this. So this is general delta phi.
That is general.
Exactly, but when we,
But that's not the crossover.
no, exactly, that's exactly the point. Because when we vary, we compute the variation of the metric tensor and its own conjugate with respect to no the change of coordinates that I set to be x prime, xa minus na. So actually we are changing coordinate that's a diffeomorphism, passive diffeomorphism. So in this particular case of change of coordinates, we have that can be expressed as a d derivative. And so, well, that such a variation is a d derivative.
Any change of coordinates can be expressed as a derivative, but you know your arbitrary variation of phi doesn't have to be a change of coordinates.
No, in our case, we set in our particular case and see what happened when we change the coordinates. That's the stuff, because actually we could just say, without saying anything there, we compute all of this that can be done, of course, without knowing that, and we get to this. And from this, we say, well, that's exactly the variation of phi when we change the coordinates. And so maybe it could be the other way around, like first we say this and say, oh, well, let's compute the variation when we change the coordinates. Maybe that's another way of saying.
Okay, I mean, this is just a discussion to show that when you change coordinates, tensors transform the derivative. Yes, that's what you showed.
Yeah.
And then you're finding a derivative.
Yeah, that's connected to the
Good
diffeomorphism constraint, and so this is, of course, the diffeomorphism constraints exists here because you know, in general relativity, the whole theory is generally covariant, so it's invariant under diffeomorphisms, and we will find this in another soup that's in the Hamiltonian formalism, but still a constraint generates, I mean, it exists because there is some symmetry in the theory. And in our case, that's the spatial here, diffeomorphism. We're saying that on the sigma, if you remember the sigma space like hyperspaces and one-time direction, on those sigma, we have again diffeomorphisms. Again, and the theory is still invariant under the subgroup of the diffeomorphisms of the total space-time. Well, this is for the diffeomorphism constraint. If we compute with H, that is only with the scalar constraint, actually it gives us something more tricky to understand, but actually it says that there is also, say, an invariant of this of the theory along the time direction that we set in the 3+1 splitting. Okay, so now, this actually, but I thought it was only 20 minutes. Actually, one. But I mean, at least slowly but surely, we give a meaning of what we're doing. Um, then- Yes, that's it. Now, tell me if you want that I continue, or if you're tired, something like that. I can continue for 20 minutes, so 1 hour.
Another 120 minutes, which is like 70 minutes, or is it like really 20 minutes?
Yeah, it could be. You got me. At your choice.
20 minutes sounds okay.
I have to set the alarm. I bear it in mind. Now, in such a formalism, this in the ADM variables, actually, we have a lot of problems. We have the problem that, first of all, well, the correspondent Schrödinger equation that is also called it's called also the Einstein-Schrödinger equation. That's the Wheeler-DeWitt equation. That is just the sum of the constants acting on a function, and we would like to know the and set it to 0 so that we find the ground state. So following the Dirac's algorithm. Now the problem in that is that the function of the wave function that we want to find is actually, as far as we know, impossible to find. And there is also another problem in that that also carries over the new formalism that I wanted to introduce here, and the fact that there is no time. The problem of time in quantum gravity is maybe someone says a terrible lack of understanding what goes on in quantum theory. Some says, well, for example, Ravelli says we don't need the concept of the time. We can work without it, and just when we go into the quantum realm, we are just interested in probability amplitudes that could give us some notion of time. But actually, since we have the Hamiltonian constant is a constant that is equally 0, because general relativity is a totally constrained system. Then we have the corresponding Schrödinger equation. Well, almost doesn't make any sense because it means that Hamiltonian is no more the generator of the time evolution. So we have these two problems. Another problem is that in the ADM variables, actually, we don't have any connection associated to some compact group. Because if we want to quantize the system, for example, take the SUN, that's a compact group, and we know very well from quantum field theory how to construct a quantum theory starting from U1, SU2, SU3 connections, right? So if we are able to change the perspective so that instead of seeing the metric tensor, the component of the metric tensor, and then each conjugate momenta as just symmetric 3x3 matrices, and if we somehow can, write them in terms of some other quantity that will result in a connection, to be a connection, then from that connection we can construct a bundle that's a principal bundle, and from that we know that the structural group of the principal bundle will be an SU, say, n Lie group, as well as the fiber, of course. And from that connection, actually, we can solve the Schrödinger equation for gravity. That's the Wheeler-DeWitt equation. But that's highly trivial, so there are a lot of steps, and very careful. We have to be very careful. So in order to do that, the concept that we have to introduce is tetrad or turbine. That's the concept is quite simple, and the turbine is actually, well, a vector field defined at any point of our manifold. And we take as a manifold the sigma, so just the space-like manifold. This EI, which I running from 0 to 3 for D, okay, we start from the 4D space-time, and then we carry it over to the space only, okay, only to the 3-dimensional. For this, actually, the tensor can be written as this, and that's it means that for a fixed I, that's also called the internal index or Lorentz index. Actually, is a vector field spanning the tangent space of the space-time at a point x. And we can also construct each dual, because from the tangent space we know that there's always an isomorphism.
Again, I'm sure you mean the right thing. I mean, it's not one vector field, but four.
For each I.
Yeah.
For a fixed I,
because otherwise they couldn't span.
Yeah, sure. No, well,
If four.
there are 4 vector fields for a fixed I. It's a vector field on the tangent space of space-time. So we have 4 vector, 4 vector fields, and actually these behave as vectors in R4, as Lorentz vectors. But okay, I was saying that together with this, we also know that there is an isomorphism between the tangent space in a point and the cotangent space in the point. So from the tangent space, that all of these are cotangent space, and so instead of having a vector field, we have a one-force, and that would be this. Okay, and again, these are 4 vectors,
4-1 forms.
401 forms, yes. And such such vectors actually are a local frame. And the point is that, say, take the first one as vector field. This one actually define a parallelization that is a basis consists of vector field of the tangent space of the point. But of course, no all the manifolds admits a parallelization because there is no global vector field made. So the tetrads are only local fields. In the sense that they only admits a local parallelization of some submanifold or our manifold. So at least locally, we can always find a tetrad. And this is not only a frame, but it's an orthonormal frame. Okay, and the orthonormality of such a frame depends on which index we are working on. In the sense that this mu is a space-time index, and this I are Lorentz or internal indices. Okay, so when we act transformation on the whole space-time, we are acting on this index. If we are instead transforming something under some gauge, and we'll see that our rotation is that, for example, then we are only acting on internal indices. And so the orthonormality is defined the triangle delta of Pi acting on J by
That's not really the orthonormality. That's just the dual basis. I mean, this doesn't mean that the E's are orthonormal.
actually, yes,
No.
because
Or, I mean, you're using the same notation, so you're using the same letter. I mean, the one forms and the vector fields.
yeah,
You can always choose to be orthogonal to each other. I mean, that's the sort of
yeah,
that's
but
the
now
definition of the dual map. You have
it's connected to.
basis in one, and you choose
Yeah,
the dual
but-
basis, which is just.
And now I want to show that it's for the dual we don't need actually a metric, but in our case we also use the metric. So
What,
that
what do you mean for the dual? Which is the dual?
well, this is the dual of the vector field.
Yeah. Okay.
So well, of course, when we act, and now I'm going to do this. It is when we want to act. Of course, that's at the same point. This mu on mu j j. Of course, by duality, this one forms takes a vector
Yeah,
field.
but you know, this is not called orthonormal. This is not the reason why you call E an orthonormal frame.
I'm going to show why orthonormal.
This is something else. This is not orthonormal.
So when this one for acting on this, actually we have the Dirac, the current delta between mu and mu, and so actually we will contract mu and mu here, so that this is given by this. So the contraction in the space-time indices. In this sense, it's orthonormal.
Don't use the word orthonormal. The orthonormal in this context is something else. And if you're using it here, then you're just going to make people confused. This is not what you mean orthonormal. Orthonormal frame is when the EI vector fields, as vector fields, using the metric,
Yeah,
are orthonormal. Using the metric. Here you don't need a metric. There's no metric here.
Exactly. But this turns out to be also true when you use the metric.
That doesn't matter. Or to say that something is orthonormal, you have to use the metric. Those vector fields are orthonormal with respect to the metric. This is not important for that. This is a trivial thing. You can always invert this matrix EI mu and define one forms. That's fine. Doesn't mean that they are orthonormal. You can't even say, I mean, a vector field can never be orthonormal to one form.
Yeah.
Only vector fields are orthonormal.
Yes, of course. That's
or
true.
one form could possibly be orthonormal also.
That's
But
true.
they can't be orthonormal with each other. So the word orthonormal comes later.
Yeah.
This is just a definition of a dual basis.
Yeah.
Just think of it in general.
Yeah, sure. That's as I said, for orthonormality, I mean, for the dual, we don't need a metric, but for orthonormality, we need a metric.
Yes.
But I'm going to say that yes, on this we have just a dual, but when we use the metric, we'll see that this condition has to be used in order to say that two such vectors are orthonormal.
No. No.
No,
No.
this
No.
is not definition.
It's completely separate.
Don't you want to say something about when you have a metric or vector space and you use duality, then you can also use the triple rules or something? Because as they said, this has nothing to do with autonomy.
It's just that the formula looks similar. Don't you have different, this is conjective.
Well, but you know the point is that here we can use the metric G mu nu to raise or lower the indices. But not.
You haven't shown that yet. No.
Yeah, but
No. No. Then you're implying that one is mapped to the other by the metric, but that's orthogonality. You cannot use that before you prove it. It's not obvious.
okay, yeah, I have to show that with the metric, by means of the metric, we can raise and lower indices so that you know, how to say, that this is exactly a scalar product induced by the metric.
No, this is not a scalar product induced by the metric.
Well,
These two guys,
not here.
these two guys do not have to be orthonormal. Sorry, the E's by themselves, vector fields, they don't have to be orthonormal. The E1 forms don't have to be orthonormal.
Yeah, this structure exists without a metric
Yeah,
at this point.
yeah, and they don't have to be orthonormal by themselves. And if they are not, then you would have to be more careful. So, you know, you have to. You're trying to take the road in the wrong order. So you're trying to go in the wrong direction.
Yeah, I agree.
Right? So what does it mean for that to be orthonormal?
Yeah,
Well,
the
you
fa-
put in the vector field EI and the vector field EJ in the metric, and
Yeah.
you measure their
That's-
scalar product. And if it's a delta, then they are orthonormal.
That's what I was going to do. Is if we write the metric enter as G mu G mu, and then we know that G mu is just G with the mu set to vector fields, and then if we use well, instead of putting this the mu inside the metric, we put exactly EI and EJ as vector fields inside it, so that we have G of mu and of course these two can be by the product, and so we have mu J and G mu here. And now this is for these two general tetrads, but if you want to look at locally, a local basis, that is that G can also be written as theta ij, where theta ij is.
Why can it be written as this?
Wait.
Yeah, this is not.
Well,
This is not true. Why? Why should it be able to do this?
because
Here you have made an assumption. This is not true naively with what you have said so far. This is an assumption. This is assuming already that.
well, instead of choosing for Pollari basis, that we can write as one forms. We can write as
I mean, I can choose for my to write EI. The matrix EI mu is just an invertible matrix.
yes,
That's it. Doesn't have to satisfy anything else. Just an invertible matrix.
yes. It's,
Right? So that means that this doesn't necessarily be. It's true. It's true only for particular choices of the EI mu. Only for particular choices. And
Well,
choices such that these vector fields
the-
are orthonormal.
Which means that the line above is equal to the.
yeah, exactly. Yeah, that's
You need to put that.
yeah. That's yeah. I mean, I said I have to set the orthonormality here.
Right. Right? Yes, if you say that,
That's the
then yes, then this is also true if you're choosing the other ones to be inverses.
And the dual basis never appears in that.
Yeah.
Well,
You said
that's
that
true, but
there is an interesting question. So if you're using the tetrad formalism, where do you assume that your connection is metric? You know?
well, I have to extend the compatibility of the affine connection on the tetrads.
Right. Okay. Let's talk about that later.
Well,
it's-
the point is that we can write by this relation that G mu nu just by inverting these matrices as eta ij and the other side.
Right.
So
And then you get that.
yeah, and no, well, I was answering to your question.
Yeah. Okay. But let's do that later. It will lead somewhere wrong. I think your 20 minutes is
Maybe over.
or are up. So that would lead to far.
Yeah, but okay, the point is just that this G mu nu that from this can be written as this also means that it can be viewed as a locally flat metric, right? In terms of, I mean, written as this in terms of these orthonormal vector fields, tetrads. Well, a way of saying, I mean, the geometric concept behind this is also that since these tetrads are locally defined, okay, and they span the yeah, it's a set of 4 vector fields spanning the tangent space at a point. It's like we are seeing locally in a neighborhood of a point that the metric is locally flat. That's another way of seeing it.
No.
No, but
Flat is not the correct word. Flat is not the correct word.
not approaching eta, not approaching the Minkowski metric, but saying that I have to use other words. That we are looking only at a neighborhood, very small neighborhood of a point, and well, we see this. So because we can also invert the Minkowski matrix so that eta ij would be, yeah, I mean that's this one from this one, that I mean the scalar product given by the metric of such fields is something giving the Minkowski matrix, so that's flat in that sense.
No,
There's no physical conflict.
no. I mean, I think again, you're probably mixing up two things. So these are not usually coordinate vector fields. There are no coordinates
Exactly, there are no.
that you can choose which correspond to this because they don't commute the E vector fields. So you can choose coordinates corresponding to them where G would be eta. There's a different question you can ask. Can I choose coordinates in which at the point G is equal to eta at the point? And that question is, the answer to that question is yes, but this is not the answer. This is not the proof of that. It does not have anything to do with that. So just from the existence of the E vector fields, you cannot say that you can choose coordinates at a point in which the metric looks like the Minkowski metric. It doesn't follow. So I think you're probably trying to say something like that, but the discussion would have to be different. So the metric eta is not a metric on the manifold, it's a metric on the tangent space where you have these orthonormal vector fields. It's eta because they are orthonormal.
Yes, I mean,
It's your choice, it doesn't have anything to do with the geometry of the manifold.
Well, I tell you honestly that I mean that's something that I understood because in so many paper you see that the people say maybe in a silly way, maybe omitting too many things. But you can find, I think, pretty everywhere that the tetrads are used to imagine geometrically that around a point of the manifold, since you have your tangent space that's isomorphic to Rn, it's locally flat in that sense. You know, not because there's no more curvature, of course, there's curvature.
Please show me in such a paper. Flat is definitely not the word I would use.
Maybe they don't mean the manifold is size of the tangent space is flat, which it is, because it's vector space, and then you just lift your metric to the tangent bundle, and you have these Crane fields which are sort of encoding the geometry, and instead of looking at the curve metric of the space, you're looking at the flat metric of the tangent bundle with ij indices and non-trivial maps which lift you from the geometry to a tangent space. But
Yeah,
you can never say that the space alternative is locally flat, because that's a different thing. That's a different sort of.
No, in the sense that we can pass from the tangent space point to R4, okay, because there is an isomorphism, and yeah, in that sense, we are seeing this vector field as I mean EI as 4 vector field in R4 using the Minkowski metric.
This doesn't say anything. It doesn't mean that the space is flat. I can compute at that point. I can compute the Ricci scalar.
Yeah,
That doesn't change. I can change
that's why we have general relativity. I mean, because
yeah. So, but flat means no curvature. So it means
yeah, exactly.
So flat is not the correct word to use. Not even at the point.
The word is not correct.
Yeah, so that's why I think either the papers are talking about something else, or well, I mean, this is a topic where there are a lot of confusing papers historically and otherwise. And physicists have not been the best in keeping a consistent language about this. So there can be wrong papers. That's certainly good.
Well, okay, but the point is to in our neighborhood of our manifold, then there exists an isomorphism from that to R4.
No, that's just
and that's the fact that we look at these vector fields as spanning R4, which is flat I meant
doesn't have to
this.
be flat. R4 is just topology. It doesn't have to be flat.
Well, with the Minkowski metric, of course.
Yeah, but that's not true.
But
Of course, the tangent space.
The tangent space
It's flat by definition, but it's got nothing to do with the east. The east don't add any more physical content, so.
Yeah, the tangent space is flat always. In that sense.
It's just by definition.
all right. Then okay, I think it's
Maybe they're using words like flat index or tangent index, which makes sense, but it's not like flat manifold, right? It's just that you're describing it by something flat.
well.
You still need to account for the curvature.
I mean, I was saying this is general relativity, and general relativity exists exactly because I mean a general manifold cannot be locally flat. I mean, generally it's not locally flat because we always have a curvature. Always, we often have curvature describing also neighborhood of a point. But yeah, maybe the words I use are misleading, confusing.
Yeah, I mean, there are a lot of confusing even books on this topic. I think all discussions on this are useful because you're trying to convince us of something, we're saying we don't believe it, and we have to go back, think about it some more, and I think, you know, you will, after a while, be convinced that this is the point where you start. You take your vector fields, E, I, E, J, and you choose them to be orthogonal. That you can do. That's your choice. And if you have them, then this is true. And you can, again, you can go between G and I and eta and use them depending on which basis you use. If you use a coordinate basis or you use the orthonormal basis. And I think you will, I hope you will let us convince you that that's the correct way of seeing things.
Well, because the tetrads also, I mean, well, if we take them to be one forms there, so the third line, actually, such tetrads are also called soldering forms. By soldering form, I mean that a solder form takes an element of the tangent space at a point, because that's a one form there, but it sends to the vertical space of the principal bundle of the frames, basically. So all that we are saying that they form a frame. That's just the section of the frame. And in that sense, I mean, we have as a structure group, the general linear group, and from that, you know, that the vertical space. I mean, we also take in the fiber that's a principal bundle of the frames. And in that sense, the vertical that consists of the tangent of the fibers, that can be regarded as the Lie algebra of the general linear group. And in that sense, we see that, that's a linear transformation of the frames, because that's a structural group acting on the fibers. And if I've been clear, they define a frame because of such a structure of the bundle. And of course, when you are taking the section at a point or a bundle, a point on a bundle, then in that case you have a frame, and that's isomorphic to what was that, to Rn squared, if I remember right, for the general linear group.
This doesn't really help.
It's just a different way of looking at it.
Yeah, try to. I think you're doing the right things. You're taking the formulas, you're trying to interpret them, and because it's kind of complicated, you might end up thinking, well, this is first, and then that implies this, when it's really the opposite. That happens. So, take the formulas again, look at them again, and then say, maybe, I start over there and go there. And then it works much better. So, you just change your point of view a little bit. To talk about the frame bundle and so on, okay, that's fine, but that doesn't really help you in calculating everything.
Yeah, that's a way of seeing mathematically the meaning of such a frame. Why it's a frame?
Yeah, it doesn't really help me anyway. But but this is something that's complicated, and it needs thinking about many times before you find something which works. Okay, thank you.
Okay, thank you, speaker. Do you have any questions or comments? I suggest you go visit Mikhail directly, you have to explain everything to that thing. He's the main man in the consortium.
No.
Yeah, and the recording.